Okay, so we're going to talk about power a little bit more here. And I know we've spent a lot of time and a lot of lesson time here doing examples and really talking about charge, current, voltage, and power. But these are fundamental concepts that we really make sure we understand, just to make this course easier, but also to make any of your future courses easier. So let's talk about power again here. And we're going to have here, I'm just going to have one device here, and then I'm going to make up several cases so we can talk about what's going on in each case. Um, I don't know why I drew it so big here, but that's fine. So we're going to compute the power, and then also is device absorbing or delivering power. So the first case we're going to do here is we're going to let V1 equal 5 volts, and then I1 is going to be equal to 2 milliamps. Now, the nice thing here when doing this computation, here again, the power is an easy computation, but one thing you always want to make sure when you do this power computation is you want to make sure that the arrow of the current is entering the positive terminal of your voltage, because that's how our equation for power was defined. So I1 is entering and hitting the positive terminal of this voltage V1. So we do know that power then is simply 5 times 2 milliamps, which would be 5 volts times 2 milliamps, which would simply just be 10. Now, you can do the scientific and everything, but you can know that volt times amps is just watts, and so we wind up with 10 milliwatts as our final power. Now, again, we don't write the positive, but since it's positive, we know that this is absorbing. All right, now let's look at another case here. So for this one, we're going to let V1 equal negative 3 volts and I1 equal 2 amps. Now, you might say, oh wait, V1 is negative, I have to do something with it. No, V1 being negative 3 volts is fine. Voltage can be positive or negative, and it doesn't matter. You might say, well wait, but the positive terminal, it can't be negative that way. The way we define plus and minus is just how we measure the voltage. It's not saying that it's a positive voltage or a negative voltage. This plus and minus is only referring to if I were to hook up a voltmeter, this is how I'd hook it up. I'd put the positive terminal up here, and I'd put the negative terminal down here, and I'd see what the voltage reading is. So these plus and minuses don't tell me that the voltage is positive or negative. All they do is tell me how to measure it. And in this case, when we measured, I'm just obviously making the numbers up, but when we measured it, we got negative 3 volts. And then the current, of course, is 2 amps. That's what we said. So in this case, the power would simply be negative 3 volts times 2 amps, which would be negative 6 watts. Now, negative power is fine. Now, when you get a negative power, though, that means you're not absorbing power. This means we are delivering power. And this would make sense, like if you're looking at, again, going back to maybe your car as an example, or actually instead of a car, let's go back to your, like a cell phone, for instance. So when you're using your cell phone throughout the day, you have a battery there, and that battery is, of course, delivering power to your circuitry. So if we were to measure the power across that battery, it would be a negative power because it's, in essence, that battery is losing power. It's getting drained from power because it's using that power and giving that energy, transferring that energy to circuit elements so that, of course, you can use your phone. And then, of course, when the power of that battery goes out, you recharge your phone. All right, now let's look at one more example here. That's one that sometimes gets people a little messed up here. So we'll look at V1. In this case, we'll say, let's just go ahead and give this a smaller number here. So this is 20 millivolts. And then what we're going to do is we're going to say I2 is 1 milliamp. Now, first off, we have to be careful with how we compute this power. I will write down something. You might not want to put this in your notes. I see a lot of people saying P is just equal to 20 millivolts times 1 milliamp. And this is wrong. And you might say, well, wait a minute, it's just voltage times current. But remember, our equation for power equals current times voltage. I must flow in to positive terminal of the voltage. But if I look at what's going on here, this I, it's not going into the positive terminal of the voltage. In fact, it's leaving the positive terminal of the voltage. But that's not a big deal. I1, of course, is going into the positive terminal. And we can clearly just see here that, well, I1 is simply going to be negative 1 milliamp. Because remember, we can simply just flip the direction of the current, and it becomes negative, but we can always just flip the direction of the current to get the correct value for it that we need for our equations. So in this case here, power would be 20 millivolts times negative 1 milliamp. Now, you need to be careful. I'm assuming you can use calculators and scientific notation. This course is really not to remind you how to do things of that nature, but be careful with your computations here. And you can always use a calculator again to help, but you would get minus 20 microwatts. And I'm going to just double check just to make sure here that that's what you should get. But if I do that in my head correctly, that is what we should have. Yes, and that is indeed what you get. And now as far as if this is delivering or absorbing power, this, because it's negative, again, because it's negative, that means it's delivering power. Now, one final comment I want to make here, and this is actually pretty critical, and then we'll start getting into some circuit elements and some circuit analysis here to be able to look at circuits. The final comment here is that in any circuit, the power delivered must equal the power absorbed. Now, let me give you a case that sometimes messes people up here. And explain sometimes why we have to be careful with this. Let's suppose we have a voltage source delivering 60 watts of power to and I'll even say we'll do an LED. Well, actually, instead of 60 watts, let's do 10 watts of power to an LED light bulb. The light bulb absorbs 9 watts of power. Have we broken the rule that power absorbed equals power delivered? And the problem hasn't given us all the information. The real answer is no. You might say, well, wait, where's one? And my question is, well, where does the 1 watt of power go? It has to go somewhere. It's not going into the light bulb. And I'm not going to answer that for you, because that's going to be part of a question we have on either a homework assignment or a discussion board. And we will answer it as a class, or I will provide the answer eventually, but I'm not going to put it in this video. I want you to think about this. Where does that 1 watt of power go? Because it has to go somewhere. Can't just magically just somehow disappear. We have to have conservation of power. But that does happen sometimes, where you have a 10 watt being delivered to a light bulb, but only 9 watts being absorbed by the light bulb. All right? So think about that, and in the next videos we will be starting with Ohm's law. Sorry about that.